Hi, and welcome to this section of the Chemistry Tutor. In this section, we're going to conquer the topic of Avogadro's number and the mole. And I have to say, this is the first section in chemistry where a lot of students really their eyes glaze over and they're like, what are they talking about? Avogadro's number is a big word, and we'll see here in a second, it's a very big number and it's kind of mystical, and a lot of students don't quite understand why it's important. The second thing is, we've got this thing called a mole. So it doesn't sound like anything to do with chemistry, but it's so incredibly important to the study of chemistry, but yet it's so kind of, again, mysterious. People don't usually understand in the beginning why it's important. So what I'm going to try to do is break it down into the simplest possible explanation that I can. I'm going to warn you though, some of it you're just going to have to sort of trust me on and trust your book on and trust the scientists before you on, because you could dive really deep into the theory of why a mole is really significant. But at the end of the day, is like, what is it used for? I mean, a long time ago, you were taught multiplication, right? And you may not have totally understood that it was a shortcut for addition for a long time, but you memorized those multiplication tables and you pretty much trusted the grown-ups that it was really important. And I think now you can see how important multiplication is, right? It's the same thing with the mole and with Avogadro's number. When you first learn it, you're like, where are they coming up with this and why is it important? I don't understand this at all. But then I promise you, a couple more months into your study of chemistry, or even a couple weeks, when we start talking about reactions and predicting what's going to pop out the other end of a reaction, and things of that nature, the mole and Avogadro's number is probably one of the most central things in chemistry. And you will be using these concepts pretty much every section. When you calculate almost anything in chemistry, it will involve a mole of something. So let's dispense with the mystery and try to tell you what this means. In a nutshell, you can read the definitions in your book. In a nutshell, a mole, right, M-O-L-E, a mole of any substance is 6.02 times 10 to the 23rd elementary units of that substance, right? One more time, a mole is 6.02 times 10 to the 23rd elementary units of that substance. So what this is saying is a mole is a huge number of units of a substance, right? And this number, this 6.02 times 10 to the 23rd, defines what a mole is, how many objects, so to speak, make up a mole, right? And Avogadro's number is what this number really is. It's named after the man who discovered it. Avogadro invented the concept, decided and showed how it was important, so he gets the honor of having it named after him. So those two concepts are really the same thing. But if you understand what a mole is, you understand what Avogadro's number is, because Avogadro's number is just the number, 6.02 times 10 to the 23rd. Now in your book, you might find a mole with more decimal places, maybe 6.022 and some other digits times 10 to the 23rd. That's fine, but when most of your calculations, you can pretty much use 6.02 times 10 to the 23rd. You can even program that number in your calculator, so it's handy for all of your calculations. So, Avogadro's number. Avogadro's number. And my definition is not going to be lengthy or wordy or anything. It's going to be practical. What this means is, we abbreviate it as NA. This means number, this means Avogadro. So Avogadro's number, that's why it's called NA. 6.02 times 10 to the 23rd. Now, this is a big number, 6.02 times 10 to the 23rd, what? What it means is, and I'm going to change colors to write the units, and I'm going to put it in quotes, elementary units per mole. So what it is defining what a mole is. One mole of something is 6.02 times 10 to the 23rd elementary unit. So it's the same way of saying the same thing. Avogadro's number is 6.02 times 10 to the 23rd elementary units per mole. That's what it basically means. So one mole of something is always going to contain this many things. Now, what do we mean by elementary units? We're not talking about, I haven't even mentioned molecules or anything, so you're wondering, what does that mean? Well, it's kind of a arbitrary thing, and it applies to everything in chemistry, atoms, molecules, or whatever. And the best way to think of Avogadro's number really is to think about a dozen of eggs, right? So you know how many eggs are in the carton. Sometimes we like to count in terms of dozens, though. We might say, hey, give me 2 dozen donuts, give me 3 dozen eggs, okay? And everybody knows that there's 12 eggs in a dozen. Why is 12 significant? Well, you could look at the history of that. I mean, there is a history, bakers and baker's dozen and all that stuff. You could go figure out why a dozen was important, but that's kind of irrelevant. Nowadays, a dozen is basically all used around us, so we frequently use units of a dozen, right? And so the same thing is going to happen with the mole. 6.02 times 10 to the 23rd is such a number that has become so ingrained in chemistry and so useful that frequently you don't even talk about molecules a lot of times. You say, give me 2 moles of sodium chloride, or give me 2 moles of hydrogen, or give me 16.5 moles of calcium, right? That's very common. And so you frequently are dealing with the unit of a mole as in an amount of a substance. And the reason you can do that is because a mole is defined to be so many elementary units. Now let's talk about this elementary unit thing. The bottom line is an elementary unit can be, right? It can be lots of things. It can be an atom. It can be a molecule. If it's a molecular compound, it could be a formula unit. So if you're talking about atoms of hydrogen, or let's say atoms of lithium or something, then when you have a mole of it, you'll have 6.02 times 10 to the 23rd atoms of lithium. That's what you mean when you're talking about atoms of lithium. If you're talking about a molecule of some kind, like water, and you have a mole of water, you'll have 6.02 times 10 to the 23rd molecules of water, right? If you're talking about something that's an ionic compound, like table salt, like sodium chloride, or calcium chloride, or something like that, then you would say 1 mole is 6.02 times 10 to the 23rd formula units of calcium chloride, or whatever. So really, the unit of a mole, that's why they call it elementary units. You can't really say it's the number of atoms or the number of molecules, because it applies to all of them. It's a way of measuring whatever you have in the laboratory. If you have a bucket of calcium atoms, pure calcium, right, then a mole is going to be 6.02 times 10 to the 23rd atoms of that calcium. If you have a bucket of some molecule, nitrous oxide, right, or it would be a tank of nitrous oxide, I guess, then if you get a mole of nitrous oxide, it's 6.02 times 10 to the 23rd molecules of nitrous oxide. If you have calcium perchlorate up in a jar in your thing, and you get 2 moles of it, then you have 2 times 6.02 times 10 to the 23rd formula units of that substance, right? So it's really the same thing, but the books, because they differentiate between molecules and atoms and formula units, it makes it sound so hard, but really it's all the same thing. It's just the mole is referencing whatever unit you have in your bucket. If it's atoms, molecules, whatever, that's why they write the definition in terms of formula or in terms of elementary units. So to kind of drill this in just a little bit more, kind of get a little bit of practice before we do some real problems. 1 mole of lithium atoms is equal to 6.02 times 10 to the 23rd lithium atoms. So you could literally buy lithium by the mole. You could go to a chemical supply company and say, give me 3 moles of lithium, and they would know that it's 6.02 times 10 to the 23rd lithium atoms for every one of those moles. So if I want 3 moles of it, I'm going to multiply by 3, right? If I want 1 mole of hydrogen molecules, this is a diatomic molecule, so when you get hydrogen, it's always bonded to itself. Then what you're going to have is 6.02 times 10 to the 23rd H2 molecules. Okay? Now what if we wanted 2 moles of oxygen molecules? Then what you would have is 2 times 6.02 times 10 to the 23rd molecules. Okay? And then just one more example, since this is an ionic compound, 1 mole of sodium chloride. This is an ionic because it's a metal plus a nonmetal. And what you would have here would be 6.02 times, since it's 1 mole, 10 to the 23rd NaCl formula units. So that's why the definition references elementary units, because if you're talking about a mole of atoms, then the unit that you have is atoms. If you're talking about a mole of molecules, the unit that you have is molecules. One more thing I want to talk about before we work problems. That is the concept of what we're going to call the molar mass. The molar mass. It's so incredibly important. Remember, just in the last section, we just talked about in the last section that you can read the numbers on the periodic table, like hydrogen, the atomic mass of hydrogen, 1.008, right? Atomic mass units. The atomic mass unit is a nice construct. It's telling us what the mass of that atom is. And helium is more than hydrogen, and you go over and over in the periodic table, the atomic masses get higher and higher. It's a relative mass. It's basically telling you how much more massive an atom is compared to another atom. It tells you at a glance that lithium is much less massive than aluminum, because you can see that their atomic masses are so much different from one another. But it's a relative mass. It's not the grams of an atom that you're measuring there. It's a relative thing, because it doesn't make much sense to measure the grams of one particular atom, because the number would be so small. What's the mass of one atom in grams? Very, very hard to do. But here we're going to tie in the idea of grams and measuring things with things we can use in the lab with the mole, right? And so what we end up with is the molar mass, right? So in the last section we talked about molecular mass. Here we're talking about molar mass, but you're going to find it's not a big deal, right? So if you look on the periodic table, I'm going to draw a crude diagram of our favorite element, hydrogen, right? So there's a big H in the middle. And above it, somewhere, usually, there's a 1, because the atomic number of hydrogen is 1. And somewhere below it, there's another number, 1.0079. Your periodic table may have less digits or more digits, but that's basically the atomic mass. Prior to this lesson, like in the last lesson, we were using this all the time. And we were basically saying that this number here is, it means... What does this number mean? We already know that it means that it's 1.0079 atomic mass units for one hydrogen atom. So what this is it's really the mass of one atom. It's just that the units are in these funky atomic mass units that are, kind of invented for chemistry, right? But here we're going to expand your mind and tell you that this number in the periodic table also means something more than what this definition is here. So definitely don't flush what we've learned. All that stuff's true. But this number has significance more than this. And what it also means is the following. It also means for hydrogen, also means that 1.0079 grams of hydrogen for 1 mole of hydrogen atoms, right? Make sure you look at that. It's super, super important. What this is telling you is, see, in the previous definition, this was the mass of one atom of hydrogen. Zoom in really tiny, that's the mass of it, right? But it's atomic mass units. It's this funky scale we invented. What this is telling us is that these atomic masses are also telling you the mass in grams of 1 mole of these atoms. 1 mole. And we know what a mole is. We just defined it to be 6.02 times 10 to the 23rd atoms. In this case, because we're talking about atoms, right? And this holds true of all of the elements on the periodic table. So if you want to measure a mole of hydrogen, right, because you might order a mole of hydrogen from a chemical supply company, then all you would need to do is measure 1.0079 grams of it, and you can do that on a balance. You can measure the number of grams on a balance. So that is what allows you to tie the real world, which is masses and balances, things we can measure, with the molecular world, which is number of molecules or number of atoms, right? Because I would never be able to count out 6.02 times 10 to the 23rd atoms of hydrogen. I mean, there's no way. You can't just count them, right? So the only thing you can do is measure them somehow. The periodic table serves that as that bridge, because all of these atomic masses here double in meaning. The first meaning is it's the mass in atomic mass units of one of those atoms. The second meaning, the one that we're learning today, is it also means that if you take 1 mole of this element, 1 mole of this element, this will be the number of grams that you have to measure out. It's so incredibly important that they give it a name. It's called the molar mass. Sounds like a funny name, like you have a mole on your skin or something, and it's the mass of a mole. But basically what it is, it's exactly what it's saying. It's the mass of 1 mole of the substance. So it's the mass of 1 mole of the substance. And this is grams per mole. How many grams per mole? Not kilograms, grams per mole. All right, so that's what the molar mass is. So on your test, if a teacher, might say, hey, what is the mass of 1 mole of hydrogen? Then you just literally read it off the periodic table. 1 mole is this many grams. Let me give you some more examples. Okay, so if you open your periodic table, and look at helium and read its atomic mass, what you will get is 4.00260. Prior to this lecture, you would have interpreted that, and it's still perfectly valid to interpret it. It is this 4.00260 atomic mass units for one atom of helium. But it also has a meaning, and that means that for helium, it's 4.00260 grams per mole. Grams per mole of what? Grams per mole of helium. So if I take and I measure this many grams of helium on a balance, I'm going to have exactly 1 mole of helium. And 1 mole of helium is 6.02 times 10 to the 23rd. I keep saying these things over and over, mainly to drill it in your head so you don't have to memorize them. So forgive me if I repeat myself a little bit, but it's just because I'm trying to get you to learn it without having to study and memorize it. All right? And this is grams per mole of helium atoms. The elementary unit here is an atom because we're talking about helium. What about lithium? That's another element of the periodic table. And the atomic mass there is 6.941. Prior to this lesson, you would have interpreted this to mean, okay, the lithium atom is 6.941 atomic mass units. But it has a double meaning. That means that lithium is 6.941 grams for every single mole of lithium atoms. So if I want to measure 1 mole of lithium atoms in a lab, I just go measure this many grams of lithium. If I want to measure 2 moles of lithium atoms in the lab, I just measure this times 2. That would be the number of grams, because this is this many grams per every single mole I measure out is 6.941 grams. So if I want to double the moles, I've got to double that measurement. Okay, so in summary, to tie it all home, the molar mass really ties the periodic table to grams, so that we can basically measure these things, because that's what we use in real life. If we're doing a chemical experiment or a reaction, we don't have a mass, a balance in the lab that measures atomic mass units. We don't have it. So when we measure things, we're not really interested in the mass of one little atom. We're usually getting a pile of powder out and then shoving it in a reaction chamber. So this allows us to tie the periodic table back to the real world, which is measuring grams and kilograms and things like that. So when you're doing your chemical reactions later, you're going to be measuring the grams of this, the grams of that, and you're going to be calculating what's going to be produced in the grams of the outcome. The molar mass is what allows that to happen, because it's the only thing that ties the periodic table back to grams. This mole is an intermediate standard saying that, okay, everything you measure for a mole of it is going to be 6.02 times 10 to the 23rd units. And if we're talking about atoms, then the unit is the atom. If we're talking about water molecules, then the unit is the molecule, and so on. So what we're going to do now is some problems. I think it's so important to understand this for 2 reasons. The mole and the molar mass are used in every section from chemistry here on out. So we're going to do a lot of practice for that reason. Number 2, here is where we're really going to start harping on the unit conversion technique that I taught several lessons ago in the other DVD, right, of Chemistry 1. I told you we were going to use it all the time, and we kind of took a detour talking about molecular names and things like that, so we didn't use it too much. But here on out, from molar mass, chemical reactions, everything that follows, we're going to be using the unit conversion technique that I outlined a long time ago. So if you haven't watched that lesson, go to the Chemistry 1, Volume 1 and watch it, or if you're watching online, go watch it online, and make sure you understand that general technique. So let's do this for this first problem. We want to find the mass in grams of the following things. All right, the first thing is 1.12 moles of CaH2. So this is a chemical formula, and what we have, or let's say the chemical supply company has delivered to us. They say, we have 1.12 moles of this stuff, which, by the way, what is a mole? This is 6.02 times 10 to the 23rd. So that times this factor of 1.12 is how many units, formula units that we have here, right? So, but we don't care about that. We want to know what the mass in grams is. So what we have to do is we have to sort of use our unit conversion. And what you're always going to end up doing is looking on the periodic table to find out what this molar mass is, and that's going to be your conversion factor. So if you look on the periodic table, calcium is 40.078. Now, we can talk about AMUs, but we're starting to transition out of AMUs. Really, when you look at this in terms of molar mass, it's grams per mole. You can also think about it in AMU, but that's not going to be helpful for this problem. Calcium is 40.078 grams for every mole of calcium. That's what that is. This is a conversion factor. It's how many grams in every one of its moles, where a mole is 6.02 times 10 to the 23rd atoms. And hydrogen is 1.00794 grams per mole. So for every mole of hydrogen, this is the number of grams. So the molar mass of CaH2 is equal to, so there's one atom of calcium, so it's 40.078, plus 2 atoms of hydrogen, which is this, 1.00794. And this is going to give us the molar mass. So CaH2 is equal to, when we do this guy, when we do this multiplication, we're going to get 2.01588. So when we add these together, we're going to get 42.094 grams per mole. Because this is grams per mole of calcium, this is grams per mole of hydrogen. So the total answer is going to be the same unit. So calcium, CaH2, is 42.094 grams for every single mole of this stuff. Now, when we say a mole, what does a mole mean in this context? It's 6.02 times 10 to the 23rd units of this compound right here. That's what it is. It's not units of calcium. It's not this many units of hydrogen. It's units of the whole thing as a unit, because that's what we're talking about here. So this is the molar mass, right? But this is an intermediate answer. This is not the answer that we really seek, because what we want to do is find the mass in grams of this many moles. So what you've done is you sort of found a conversion factor here. And to keep going, what we know is we have this many moles, 1.12 moles of CaH2. This is how many moles we have of CaH. That's what we start with. This tells us how many grams for every single mole. So we need to arrange it in a way to cancel our units, and that comes back to what we talked about before. So what we're going to end up doing is we're going to have 42.094 grams per mole of CaH2. So this cancels with this. It's 42.094 grams per mole. If we flipped it upside down on accident, then we wouldn't have the cancellation here. So if this doesn't make sense to you, this cancellation and how I did this, if this is like, what is he talking about? Please stop what you're doing now and go back to the Volume 1 of Chemistry 1, or go get my unit conversion tutor and watch it. Because I promise you, and I still mean this today after having gone through electrical engineering and physics degrees and working in industry, this technique of unit conversions, which this is quite simple looking because it's so small, but when you get to bigger ones especially, this technique is probably the single most useful thing I've ever learned in school. I mean, besides the basic math. I mean, as far as really pulling yourself out of some tough problems, knowing how to use this is going to save you. So make sure you understand it. These units cancel, so that means I need to multiply these guys together. Okay? So when I do that, when I'm to do this multiplication, what I'm going to get is 47.1 grams of CaH2. And this is the answer. The problem told us we started with 1.12 moles of it, and we've converted basically down to 47.1 grams of this stuff. So I'm not going to be able to measure moles too easily, but I can easily measure grams. I can go in the lab, and I can put it on a balance, and I can measure this many grams, and I can say, here you go, here's a bag of 1.12 moles of this stuff. Now, the unit conversion method is amazing, but it is important for you to know what you're doing. What you have here is you have this many moles of it, right? This tells you this is how many grams in every single mole. So if you had 1 mole of this stuff, you would have 42.094 grams of it. But we don't have 1 mole. We have just over a mole. So it makes sense that you would multiply those numbers together, because I actually have more, than a mole, right? So when I multiply them, I'm going to get a larger number than this, and that makes sense. It's kind of like having 2 dozen eggs. You want to know how many eggs in total you have, you multiply the numbers. 12 eggs times 2 dozen. 12 times 2, 24. Because each dozen has 12 eggs in it, right? So it's the same thing. But the problem, so to speak, is that when you get to longer and longer calculations, it's not going to be clear in the beginning if you should multiply these numbers together or divide them. Especially if I'm doing additional multiplications for, maybe a chemical reaction. Maybe we'll learn later that we'll be balancing the reaction, and we're going to be using the information about the chemical reaction to calculate the product. So this whole thing, this train, is going to get much, much longer. And it's going to become very hard for you, especially in the beginning, to know right away, should I multiply or should I divide? And you'll be thinking logically about how it should work, right? And that's important. I always encourage students to think, obviously. But the unit conversion removes any ambiguity. You start with the number of moles you have. This conversion factor is given. You have the latitude to flip it upside down however you want. I chose this way because I'm canceling the unit that I want to cancel, and I'm left with the unit that I want to have. This is my answer because the units cancel. And doing it that way is never going to give you the wrong answer. And you'll remove all that uncertainty and all of that, all that doubt. Now, I could give you a problem that would be super difficult with density and all kinds of stuff in there, and you'd have to plot a course from statement to answer. It's not hard, it's not impossible, it's just that with the unit conversion stuff, it's going to make your life so much easier. So let's figure out how many grams in 0.158 mole of the compound iodine pentafluoride. So there's a couple things going on here. First thing you have to do is look at iodine pentafluoride. What is this chemical formula? Well, iodine is just going to be I. Fluorine is F, right? And penta, like pentagon, is 5. So IF5. That's the first step, right? You have to know what you're dealing with. And we know that we're going to be going from moles to grams. So we know we need to know how many grams are in 1 mole of this substance. And the only way to do that is from the periodic table. So for iodine, when you read it off, it's 126.904, and the unit is grams per mole. So grams per mole of iodine. For fluorine, it's 18.998 grams per mole. So every single mole of fluorine, it's 18.998 grams. So we need to find the molar mass of the whole thing. And so we just add them up. So we'll have 126.904 plus 5 from this times this mass, or this molar mass, 18.998. And so what you're going to have at the end of the day is this multiplication comes out to 94.99. So at the end, for IF5, when you take this and you add this to it, what you will get is 221.894 grams per mole. Okay? 221.894 grams per mole of iodine pentafluoride. But that's not what we want. That's an intermediate answer. This is the molar mass. This is the molar mass of this compound. So on your test, if the test question was, hey, just find the molar mass of this guy, that's all you have to do. But we're not doing that. We're actually have a certain amount of this material. We want to find out how many grams we have. So the first thing you do is, when you build your little unit conversion thing, is write down what you know. 0.158 moles of this substance. I have this many moles of the substance, so I start with that on the top. And I have a conversion factor, converting grams to moles of this substance. I can flip it either way I want. But if I write it like this, 221.894 grams per mole, if I write it that way, then moles cancel with moles. If I accidentally flipped it upside down, nothing would cancel because you wouldn't have anything on the top and bottom that was in common. So when you do this multiplication, since they're on top, you multiply them, what you are going to get is 35.1 grams of iodine pentafluoride. And this is the answer. So we started with 0.158 moles, and we converted that down to this many grams of that guy. Now that makes sense because look at what we found here. For this compound, since we have 5 atoms of fluorine, it's pretty heavy. 221 and some change grams for every single mole of that. But look at what we started with. We didn't even have 1 mole. We had way less than a mole. So it makes sense that the final answer in grams is going to be less than this molar mass because we actually don't even have a whole mole to begin with. We have something much less than a mole. So at this point, you understand the fundamentals of what this section's about. I'm going to erase the board. We're going to work some more problems, change it up a little bit, different compounds, just give you a little more practice. But pat yourself on the back. Up to this point, you truly and truly do understand molar mass and how it's important and how to convert between grams and moles. And I cannot stress enough how important that is. So let's go and do that now. We'll erase the board, we'll work some more, build your skills that much more.